Hello and warm welcome to everyone to the 24th lecture on financial econometrics. In continuation of the previous lecture, today we'll discuss on the concept of stationarity. So basically we'll discuss the very important aspect of the stationarity, that is how we detect the stationarity and what are the implications of a series being stationary and non-stationary. So let us quickly revise what we mean by the stationary, non-stationary. So a series Yt is assumed to be non-stationary if the distribution of the series is not consistent over time of period. That basically we means the characteristics of a distribution, let's say mean, variance and covariance, are not consistent over a time for a particular series, then that series is called non-stationary series. That we can see by looking this particular graph. So if you see this particular graph here, if you take the same time period, let us say here, so let us say here we take the 1 year period here, this period, and the same period if we take, let us say here 1 year period. So the time width are the same, but location of time is different. From here we can observe neither the mean nor the variance or the covariance are same. So that means for this particular series, mean, variance and covariance are time dependent. So location of time does matter for this particular series, and such series is known as the non-stationarity. In opposite of that, a series Yt is assumed to be stationary if its distribution is consistent over time. So basically, this if the whole distribution is consistent, we have the concept of strict stationarity or the strong stationarity. There is a related concept what we call the weak stationarity or the covariance stationarity. So basically, in that case, not whole distribution, all the property of the distribution, rather than a certain characteristics of distribution, that is mean, variance and autocovariance are consistent over time, then we call that particular series is weak stationary or covariance stationary. Actually, in the real world, often this a series being weak stationary is sufficient for the further analysis of modeling. So basically, what we mean here, if Yt is a stationary series, then the mean of this, that is the expectation of Yt, is equal to mu, which is constant for all the time period. Similarly, the variance of the series will be also constant for all the time period, and the covariance basically depends on the time gap between the two observations, but it does not depend what is the location of time. So whether you measure from 2010 to 2020, whether 2020 to 2030, since the time gap is 10, the autocovariance will be the same. So if this three property is there, then we call it that series is weakly stationary or covariance stationary. And in most of the practical problem, we are concerned with the weak stationarity of a series. And if we plot a stationarity series, it looks like this. So here if you see, if we take the same time period, same time width in the two different places, then the mean, variance and covariance seems it is constant, it is same, despite being the two different time periods. Now the question is why we are concerned about a series to be stationary or non-stationarity. So let us talk about if the series is non-stationary, then what will happen. So in that case, what we'll see, first the effect of the shock will be permanent. That is, if there is any disturbance in the series, it will have a permanent effect. For example, let us say if the stock price, that is the data generating process of the stock price, is non-stationary, then this effect of COVID will remain always. So that will be a permanent phenomena for the particular market. Then another important implication of a series being non-stationary is the spurious regression. So basically, if we have the two non-stationary series, let us say xt and yt, and if you regress either xt on the yt or yt on xt, in that case, the results what we'll get will be misleading. So basically, In fact, there won't be any underlying theoretical relationship. However, the statistical measures will show there is the relationship. Just because these two series are non-stationary, they are having a similar trend. So, and related to the another case we have, that estimates will be inaccurate and unreliable, and so the forecast will be unreliable. So, if the series is non-stationary, these are the problem we will have, which is not desirable property of any modeling. So, let us say, for example, here the BSE 100 is the stock prices of the Bombay Stock Exchange, whereas the CPIT is basically consumer price index of the Turkey. Now we know that there is no theoretical ground to be assuming that there will be any relationship. However, from the graph we can observe both the series are non-stationary. Now in this case, if you regress BSE on the consumer price of Turkey, here what we are observing that the coefficient is high, and this coefficient is highly significant, and so the R square. So it shows that CPI of the Turkey statistically affects the BSE 100 of the Indian market. And in fact, 78% of the variation of the BSE 100 is being explained by the CPI, that is the consumer price index of the Turkey, which seems absurd because there is no any theoretical ground to be believing this particular relationship. This relationship is the example of the spurious relationship, and we often face this kind of situation when the two series are non-stationary. Now let us see the another situation here. Okay, if we are converting those series, so now we have, instead of BSE 100 prices, we are measuring as the return, and similarly CPI we are now measuring in the inflation. So basically this is the rate of change of price and the rate of change of consumer price index. So in that case, from this graph we can observe these two series basically now behaves like a stationary series. In that case, what are the advantages we have? So in case of stationary series, the statistical property of the distribution will be consistent over time, and the estimates will be reliable, and forecast will be also reliable. Now let us repeat the last example regression here. So again we are regressing RBSE, that is return of the BSE 100 on the inflation. Now we can observe from this, first there is no statistical significant relationship between these two. Second, now R square is 0.001, that is even less than 1% variation in the BSE is explained by the CPIT, which basically reflects the true nature of the relationship, because there is no any theoretical basis assuming that the consumer price index of Turkey will affect the Bombay Stock Exchange in India. So once the stationary, it shows the real. So here the estimates are reliable and accurate compared to the case of non-stationary series. Usually the non-stationary series is represented in the two models. So one, what we call the deterministic trend process, represented as yt is equal to alpha plus beta t plus ut, and another is the random walk model with drift represented as yt is equal to mu plus yt minus 1 plus ut. Both these are the different models of a non-stationary series. So here this ut follows a white normal distribution with mean 0 and variance sigma square, or we call white noise process. Now let's generalize the second case, the random walk model without drift. So we are removing the drift for the simplicity. So we are assuming yt is equal to 5 yt minus 1 plus ut. So let us assume this is the equation 1 here. So here the phi can take any value, and ut is, as usual, is a white noise process. Now we can write this here, yt minus 1 is equal to 5 yt minus 2 ut minus 1. So basically in both sides we are detecting minus 1. So yt minus 1, here yt minus 2. Similarly, yt minus 2 can be represented as 5 yt minus 3 ut minus 1. Now substituting these two values in equation 1, what we get, yt is equal to, so in place of yt minus 1 we will write this So 5 yt minus 2 plus ut minus 1. Then you multiply this, it becomes 5 square yt minus 2 plus 5 ut minus 1 plus ut. Now in place of this yt minus 2, we use this term. Then ultimately we get yt is equal to 5 cube yt minus 3, 5 square ut minus 2 plus 5 ut minus 1 plus ut. Now if we this substitution successfully t times, then we get this particular form of equation. So ultimately equation 1 with the t successive substitution turns out to be this. Here this y0 basically represents the initial value of y. Now the value or this nature of this particular equation will basically depends what is the value of phi. So here three cases we have. Depending on the value of phi, we will have three situations. So the first situation we will have where let's say phi is less than 1. If phi is less than 1, then phi to the power t will tends to 0 as t tends to infinity. That what we mean basically. Let us say if the value of phi is equal to 1, then to the power 1 equal to half. If we have 2, then it is 1 upon 4. If it is 3, then it is 1 upon 8. So as this value of t is increasing, this value is becoming less and less. Ultimately, if t reaches to infinity, this value will reach to the 0. So in that case, basically what we implies this, that the effect of shocks to the system will gradually die away. So basically here it will, the effect of the shocks will vanish as time progresses. Second case where we assume phi is equal to 1, then phi to the power t is equal to 1 for all the t. In that case, if you see here, this situation here, in that case, this effect will be basically of the shock will be persistent over the time. So whether time goes to the infinity, but the effect won't die out. So that is the basically case of the non-stationarity. So we can write in this particular case, we can write that yt is equal to y0 plus the summation of all the terms as t tends to infinity. And the third case is basically when the phi is more than 1. When phi is more than 1, it implies that as time passes, the shocks become more influential as time passes. That is, let us say if phi is equal to 2, then 2 to the power 1 is 2, 2 to the power 2 is equal to 4, 2 to the power is equal to 8. So as t increases towards to infinity, this particular term also increases towards to infinity. So the effect of the shocks will be more and more as time passes. However, we do ignore this third case on account of these two facts. First fact, this explosive behavior, why we call explosive, as time increases, the effect will be exponential will increase. So in that case, we ignore. Why we ignore this? Most of the economic and financial series do not show such kind of behavior. Third, this property does not have any intuitive approach. Why? For example, what it means? It means once you give a shock into the system, that shock not only have permanent, rather it will be increasing day by day. So now let us say what we know, if you increase FDI, that is if you give a shock to the FDI, it will increase the GDP. If this is the phenomena, that means one time increment if FDI will have infinite time increase in the GDP, and that will be also automatic, and as time passes it will be increasing. But that is not the case of the real world. So basically the third case often we ignore in the analysis. Now these two common non-stationary form needs different treatment to bring that series to the stationarity. So any series, if it is non-stationary, we can bring that to the stationary case. So the deterministic trend process, we have yt square mu plus beta t ut. This particular form could be made stationary by detrending it. However, there is a certain aspect we have to keep in mind in this case. First, we can induce the stationarity just by detrending this series, that is removing the effect of the trend. That's why it is called the deterministic non-stationarity. However, if we first difference the trend stationary series, it would remove the non-stationarity, but it will introduce an MA structure into the errors, which is again not a desirable property. Conversely, if we try to detrend a series which is a stochastic trend, then we will not remove the non-stationarity. However, often what we do here, we estimate this particular equation. So once we estimate, we will get the estimated residuals as we have discussed into the previous OLS lectures. Now, instead of YT, for further analysis, we use this estimated series which will be stationary. In the other case, in the second form, what we have this stochastic process. So in this case, by differencing this series, we will be able to introduce the stationarity. That's why it is known as the difference non-stationarity or stochastic non-stationarity. To understand that, let us say we are subtracting yt minus 1 from both sides of this equation. So we will get this particular form, yt minus 1 and mu plus yt minus 1 plus ut, and this is minus ut. So plus yt minus 1 minus yt minus 1 will be cancelled, and this we can represent delta yt, which is equal to mu plus ut. Now we know that mu is constant and ut follows a white noise process. That means this delta yt follows a white noise process, that is stationary. So in that case, this was a non-stationary series, and by differencing, we have introduced the stationarity. So we know that this series was non-stationarity. By differencing, we have introduced the stationarity into the series. Let us see how that happens in the graphical way. So basically, let us say this is the non-stationarity with the time trend. As time passes, it is upward trending here, and this is the non-stationary series. Now, if we detrend, that is, if we remove the trend, this series becomes like this, which is nothing, basically an stationary series. So by detrending a deterministic series, we made it induced a stationary. On the other hand, let us say we have this random walk non-stationary series. Now, differentiating this series, we can make it stationary like this. So basically, this series is delta yt and yt minus 1. So by differentiating the previous series, we made it a stationary series. Then the question comes, how we can detect the presence of unit rule? There are the two approaches we can adopt. One, the graphical analysis. Another is the statistical analysis. In the graphical analysis, let us say here this series we have. So we can have the same time width at the two different time location of time. So here we have the same time width and this is the same time width. Now if we are able to seek whether the mean, variance are same and the covariance are depends on the time width, not on the location of time, then we can say series is stationary. But let us see this particular series. Obviously, we can observe that the mean for this particular observations and mean for this particular observation, and so is the variance and the covariance is not same. That means this series is non-stationary. So that means the mean, variance and covariance are time dependent. However, often it is not easy to ascertain just by looking the graph. For example, let us say we are looking this. Here again the time width are the same but at the two different location of time. Now it is quite difficult to say whether the mean here and mean here are the same or different, or the variance here and here is same or different. So often it is not easy using the graphical method to ascertain the stationarity or non-stationarity property of a series. Therefore, usually we turn to the statistical approach. So, to understand the statistical approach, let us understand a concept, unit root. So, what is unit root? To understand that, let us say We have a series yt which is structured like this. Now we know that if we take the difference of this series and convert into this become a stationary. If we generalize this case, then what we have, we can define the unit root. Okay, if a non-stationary series yt must be difference d times before it becomes stationary, then it is said to be integrated of order d and written as yt is integrated of order d here. What does it mean? It basically means that if yt is integrated of order d, then it must be difference d times to make it stationary, that is integrated of I0. That means if a series is I0, that means it is a stationary series and we call it is integrated of order 0. On the other hand, if any series is integrated of I1, that means it contains a one unit root. So that means order of integration often represented with D shows the presence of number of unit roots. So for example, here it is I1, that means it contains one unit root. What we mean? That means by one time differencing, we will be able to make it stationary. So if it is I2, that means 2 times we have to make it difference. So if we write a series is integrated of order 2, that means it contains 2 roots and we have to difference 2 times to make it stationary. So there are many unit root tests we have, but the traditional unit root tests we will be discussing. There are the many types of unit root tests we have. So here basically we will discuss in this class, in this course, the traditional unit root test, that is Dickey-Fuller, augmented Dickey-Fuller, Phillips-Perron and the KPSS unit root test. So this test basically helps us to ascertain the stationarity or non-stationarity properties by ascertaining the unit roots in a series. Dickey and Fuller, they are the two economists who basically developed the first formal test to examine the non-stationarity of the series. So this is the test for the existence of a unit root. So let us write a simple AR1 process. So what is AR1? AR here basically refers auto-regressive process. So this AR1. So we call it autoregressive process of order 1. Autoregressive basically refers the series depends on its own previous observations. Order basically refers how many legs of the previous observation. So here we can say yt depends on its own leg and here there is one leg, so we call it AR1 process. So let us say you have a series yt mu plus phi 1 yt minus 1 plus ut. So here basically we are testing this phi 1 is equal to 1 or less than 1. If it is 1, that means the series is non-stationary. And if the phi is less than 1, that is stationary. So here the null hypothesis we assume phi 1 is equal to 1 and phi 1 is less than 1. So if it is less than 1, that means shocks will die out as time passes. If the phi is equal to 1, that means shocks will be permanent. So that means the series is non-stationary. However, while testing, what we do here, this equation we convert here, yt minus 1 plus mu plus phi 1 yt minus 1 plus ut. Or here we can write delta yt is equal to mu plus phi 1 minus 1 yt minus 1 plus ut. Or we can write yt is equal to mu plus gamma yt minus 1 plus ut. Now phi 1 is equal to 1 is equivalent to testing gamma is equal to 0. Since if phi is equal to 1, then phi 1 minus 1 is nothing, but it will be equal to 0, that is gamma. So instead of testing phi is equal to 1 or less than 1, we test whether gamma is 0 or it is less than 0. So here let us say the Dickey-Fuller gave the test in 1979 and he proposed 3 alternative forms that can be used to test for the presence of a unit root in a particular series. So first, no constant, no trend in the equation, that is delta yt is equal to gamma yt minus 1 plus ut. So here we test whether the gamma is equal to 0 or gamma is less than 1. Then the second form, the constant but no trend. So we have alpha 0 plus gamma yt minus 1 plus ut. Third case, both constant and trend we included here in this case. So however, in all these cases, we test only the value of gamma. However, this ADF test is appropriate when the error term is white noise. If there is the presence of autocorrelation, then the power of that test is low. To avoid that situation, the Dickey-Fuller has basically augmented. What we means augmented by means basically to take account that the test includes extra lag terms of the dependent variable to eliminate the presence of autocorrelation. So basically what we did, again 3 forms. So to avoid the presence of autocorrelation to the error term, we add this particular extra lags here. So here k is the lag, beta I is the coefficient. Then similarly we have these 3 forms. So here k is the maximum lag. Often we use the information criteria that either AIC, BIC or other information criteria to ascertain what would be the maximum lag. To including the extra lags, basically we will be able to remove the presence of autocorrelation into the error term. So what test statistics we use in both ADF Dickey-Fuller and the augmented Dickey-Fuller test statistics, that is based on the T ratio. That is, we calculate the test statistics, estimated value of gamma and standard error of that gamma. And here the statistics does not follow the usual T distribution under the null, since the null is one of non-stationarity, but rather they follow a non-standard and it is often calculated using the Monte Carlo experiments. So here the null hypothesis of unit root is rejected in favor of the stationary alternative in each case. That each case means all 3 forms of the equation if the test statistics is more negative than the critical value, or we can say if the absolute value of this test statistics is more than the tabulated value or what we call the critical value, then we call it, we reject the null and we conclude the series is stationary. So higher order of integration, what we mean higher order of integration, let us say we are estimating this equation. So here we are estimating whether the gamma is 0 or whether gamma is less than 1. If we reject, if the null meaning series is stationary, if null hypothesis is not rejected, that means the gamma is equal to 0. So implies that yt could be integrated of order 1 or more. Both cases we will be able to conclude this if you are not rejecting the null. So now we have to test whether this yt is integrated of order 1 versus the integrator of order, integrator of order 2 versus integrator of order 1. So we now regress second difference on the delta yt minus 1 plus the lag terms if necessary to remove the presence of autocorrelation. So now we test this, which is equivalent to test yt is equal to I2. So now here if we are again do not reject the null, we conclude that yt is at least IT, that is integrated of order 2, that is it contains 2 unit roots. However, most often in macroeconomic series that will not be the case. Rarely we will find any economic or financial series which will be integrated of order 2. And if we find such series, we have to be extra cautious about the result. Then another test is Phillips parent test. So this is similar to ADF test, only the difference is that to incorporate or to eliminate the presence of autocorrelation, or we can say to correct the presence of autocorrelation, in case of ADF we have added the extra leg. So here they do not add the extra leg, rather that there is the automatic correction while they calculate the statistics. So Phillips test is the same AR1 process. Let us say here only this PP test makes a correction to the T statistics of the coefficient gamma from the AR1 regression to account for the serial correlation in the UT. So instead of lag, how they calculate the test statistics, there they make the adjustment for the presence of autocorrelation. So usually it gives the same conclusion as the ADF test. Then however, this both ADF and Phillips tests are criticized for the low power. What we mean with the low power? If the process is stationary but with a root close to non-stationary bound, let us say this situation. If it is phi is equal to 1, that means series non-stationary. What if the value of phi is not exactly 1 but very close to 0.951? Sorry, 0.95. In that case, this ADF and Phillips parent often they are not able to determine, and they will conclude the series is non-stationary. However, it is non-stationary. So, and this is the problem often we face if we have this very small sample size. Now, if the true data generating process is this, the null hypothesis of unit roots should be rejected, but in case of ADF and Phillips parent, often we are not able to reject. So, what is the way out of that? So, one way out that use a stationarity test rather than a test of non-stationarity. So, what is the stationarity test? Basically, here we assume that null is YT is stationary. So, in that case, we will not able to reject the null, and that is the basically true that data generating process is stationary. Versus alternative YT is non-stationarity. So, by default under the null, the data will appear stationary. One such stationarity test is the KPSS test, where we can use this test and we can compare the results of this test with the ADF and the Phillips parent to have more reliable conclusion or inference whether the series is stationary or non-stationary. In the next lecture, basically we will implement this test on the data of the stock prices of Indian market, and we will see how we can use this test to ascertain about whether the series are stationary or non-stationarity and how we interpret the results of those series. So see you in the next class, and thank you very much.